As astrophysicists, we need to become best buddies with photons. Up until this point, we've concentrated on the theory of photons. We've taken for granted that we can detect and analyze them. But in this lecture and the next one, we'll talk about how we perform those measurements. We'll talk about the physics of telescopes. Let's start with a simple question. Why do we build telescopes? What's wrong with our eyes? Most people think the main purpose of a telescope is to magnify, to make distant objects seem closer. And it's true, telescopes magnify, which is great if you're a bird watcher or a backyard astronomer looking at a planet through an eyepiece. But for professional astronomers, magnification is one of the least important reasons to build a big telescope. To explain the most important reason, I'll start by showing you a picture of a tarsier. It's a primate from Southeast Asia. Even if you've never heard of a tarsier before, you know right away it must be nocturnal, just by looking at it. Why else would it have such enormous eyes? Tarsiers work at night, so they need to make the most of the faint light from the moon and the stars. Well, astronomers work at night too, and we need big eyes, even bigger than a tarsier's. Collecting more light improves our ability to detect faint sources and to measure their properties with greater precision. In addition to having bigger eyes, nocturnal mammals have better eyes. A tarsier's retina, the light-sensitive layer of cells at the back of the eye, has more rod cells than cone cells compared to our eyes. That makes their eyes more sensitive to photons. Likewise, astronomers use sensitive digital cameras instead of relying on our retinas. For every 100 photons that hit your retina, no more than 5 or 10 actually get registered and contribute to the signal that gets to your brain. We say that the quantum efficiency of the human eye is less than 10%. But a digital camera optimized for astronomy can have a quantum efficiency of 90%. And of course, the camera can make quantitative objective records, so you can count the number of photons that hits each pixel instead of relying on subjective visual impressions. There are a lot of other reasons to love telescopes and cameras. They give us better angular resolution than our eyes, the ability to resolve fine details. They give us better spectral resolution, the ability to distinguish different wavelengths. Better time resolution, the ability to discern changes in the brightness or color. And we can detect radiation that's invisible to our eyes, like radio waves and X-rays. Let's discuss each of these in turn, starting with the number one reason to collect more light. You can think of the light from a distant source as a gentle rain of photons falling onto the Earth's surface. When we look up, our eyes collect the rain that happens to fall through our pupils. When we're using a telescope, we're using a bigger bucket to collect that rain. As a specific example, consider Proxima Centauri, closest star to the Sun. The rain coming from Proxima Centauri amounts to about 100 photons per square centimeter per second. That might sound like a lot, but the pupils of our eyes are only 1/5 of a square centimeter, and our retinas don't respond to 90% of the photons that get in. Even worse, we only have about 1/10 of a second to detect a signal. Our visual system can't accumulate signals for longer than that. It's like a camera, but with a hardwired shutter speed. Putting all that together, the average number of photons from Proxima Centauri that enter our eyes and get detected during 1/10 of a second is 0.2. That's less than 1. And that's why Proxima Centauri is invisible to the naked eye. With a telescope and a digital camera, we can boost all the factors in this calculation. We can increase the collecting area. We can detect nearly all the photons, and we can use whatever shutter speed we want. The reason this is so important is that the rain of photons is not completely steady. There are fluctuations. Let's say we're looking at a star that's spraying our telescope with 100 photons per second on average. The crucial words are on average. Really, the number of photons arriving each second is a random number. All we can say is that given the overall luminosity of the star and its distance from Earth, the average number of photons entering our telescope is 100 per second. But in any individual second, it could be 94, 106, 120, and those fluctuations prevent us from measuring the star's brightness as precisely as we might want. Whenever we're dealing with events that occur at random times, but with a well-defined average rate, like radioactive decays, earthquakes, or the arrival of photons from a distant star, the relevant piece of mathematics is the Poisson distribution. Let's say n is the average number of events that we expect to occur in some time interval. Then the probability we will actually observe k events is n to the kth power divided by k factorial times e to the minus n. That's the Poisson distribution. Let's plot that for the case of n equals 100 photons. The horizontal axis is k, the number of photons detected, and the vertical axis is the corresponding probability. The most likely outcome is 100, but any value between 90 and 110 is also likely. Mathematically, the mean value of k, which we write as k surrounded by angle brackets, is equal to n. And the standard deviation of k, or sigma k, that's a measure of the spread in the likely values, is equal to the square root of n. In this case, the mean is 100, and the standard deviation is 10, which means there's about a 68% chance that the number of photons in our image will be between 90 and 110. And that implies our flux measurement could deviate from the average by about 10 units out of 100, or 10%. Another way to put it, the signal-to-noise ratio of the measurement is 10. Signal is the average flux of the star, and the noise refers to the random deviations from the average. Now, what if we're looking at a fainter source that only delivers an average of 25 photons to the detector? Let's replot the Poisson distribution for n equals 25. Now the mean is down to 25, and the standard deviation is 5. So the signal-to-noise ratio is 25 divided by 5, which is 5. In general, the maximum possible signal-to-noise ratio is n divided by the square root of n, that is, root n. And in fact, it's usually worse than that, because the light from your favorite star is going to be blended together with other sources of light, from nearby stars in the sky that you can't resolve with your telescope, or from the faint glow of the Earth's atmosphere. The photons from those other sources contribute to the fluctuations too. We call that sky noise. When sky noise is significant, we need to revise our signal-to-noise equation to be n divided by the square root of n plus n sky, where n sky is the number of photons from other sources besides the star. The inevitable fluctuation in the photon count, called Poisson noise, is an unforgiving fact of life in astronomy. There are lots of ways a measurement can be wrong, but even if you have perfect equipment and make no mistakes, you can't eliminate the Poisson noise. But there are ways to lower it. We can increase the exposure time, thereby increasing both n and n sky. We can use a camera that responds to a wider range of photon energies or wavelengths. That too will boost the photon count. But often these measures are not enough, and we have no choice but to build a bigger telescope. As an example, here's a series of images of a galaxy. It's the same field of view in all cases, The only thing changing is the average number of photons that contribute to each pixel. The image with the lowest photon count is grainy. Only the bright center of the galaxy is visible. The fluctuations in the light level swamp everything else. But as we increase the number of photons, the fainter spiral structure of the galaxy comes into view because the fractional level of the fluctuations is smaller. That helps to explain the constant drive to build bigger telescopes. This chart shows the diameter of the largest optical telescope in the world over the centuries, starting from Galileo's telescopes, only 10 centimeters across, to today's largest telescopes, which use mirrors 10 meters across. The vertical axis is logarithmic, which means the upward linear trend represents exponential growth. Telescopes have been doubling in size every 40 years or so. Another reason we love big telescopes is to improve our angular resolution, our ability to measure the direction from which photons are coming and make sharper images. We've already learned about the diffraction limit, the tightest possible focus that we can achieve given that light is a wave. The smallest angle we can resolve is about 1.22 lambda over d, where lambda is the wavelength and d is the diameter of the primary mirror or the lens. Visible light has a wavelength of about half a micron, and our eyes have a d of about 5 millimeters. So the diffraction limit works out to be 1.2 times 10 to the minus 4 radians, or about 25 arcseconds. Amazingly, real eyes come pretty close to this fundamental limit. Mother Nature is a good engineer. But astronomers can do better by increasing d to 10 meters, an improvement by a factor of 2,000. In that case, the equation gives delta theta min of only 0.013 arcseconds. There is a catch, though, one that we discussed earlier. Fluctuations in the temperature and the density of air produce a blurring effect of order 1 arcsecond, even on a high mountaintop. So we can't take full advantage of the large d to improve our angular resolution. Well, at least not easily. There are two ways around the problem. One is to put your telescope in space, above the air, like the famous Hubble Space Telescope. Or you can stay on the ground and use a technique called adaptive optics. Adaptive optics is when you put a deformable mirror somewhere in the light path of your telescope. Lots of mechanical actuators are mounted on the backside of the mirror, which can apply tiny localized forces under computer control, pulling and pushing by just a fraction of a micron. The goal is to distort the mirror just the right way to reverse the distorting effects of the air. You have a separate camera stare at an extremely bright star, which you know should appear as a sharp point in the image, but it doesn't because of the turbulent air. It looks like a big blotch. Then the computer measures the shape of that blotch and uses an algorithm that tells it how to distort the mirror to turn the blotch back into a point. And all of this has to happen within a few milliseconds because the atmosphere is constantly changing. It might not surprise you to learn that some of the earliest adaptive optics systems were developed by the military. They use it to resolve the details of enemy spy satellites. It became popular among astronomers starting in the 1990s. This technology allows us to get close to the diffraction limit even with a 10-meter telescope. Do you remember those images we saw of the stars orbiting Sagittarius A star, the black hole in the center of the Milky Way? Those were made with adaptive optics. Without that, all of those stars would have blurred together into a big smudge. Better angular resolution also gives us a way to reduce the Poisson noise. The reason it helps is that it improves our ability to separate the star's light from the other light sources. It reduces n-sky in our signal-to-noise equation. So in situations where the sky noise is the main problem, improving the angular resolution leads to a higher signal-to-noise ratio. Now, back to our list of the advantages of telescopes. A third reason is to improve our spectral resolution. By that I mean our ability to measure the energies or the wavelengths of the incoming photons. Our eyes can sense millions of different colors and make very fine distinctions between photons with wavelengths ranging from about 0.4 to 0.7 microns. I've always found it fascinating that we don't perceive the rainbow as the simple linear scale that it is. The wavelength varies monotonically from one end to the other. Instead, our eyes go on a wild ride through all kinds of different sensations: red to orange, yellow, green, and blue. But as miraculous as color vision is, our eyes can't analyze those different hues in any quantitative way, and certainly not in low light, when our vision is basically black and white. With a telescope, we can distinguish colors in several different ways. We could put colored filters in the light path that admit only the light within a narrow range of wavelengths. Then we can take exposures through different filters and combine them, sort of like how our brains combine the signals from red, blue, and green sensitive cells. Or if we want to make finer distinctions, we can put a prism in the light path, which deflects the light by an amount that depends on wavelength. That way the light from a star, instead of appearing as a point in the image, shows up as a little stripe of light, a miniature rainbow. Now, if there are other stars nearby, we wouldn't want all those rainbows to overlap. That would be confusing. So before the beam of light reaches the prism, we interrupt it with an opaque sheet with a slit in it and position the slit so that the light from our favorite star or galaxy or whatever goes right through the slit, and all the other sources of light are blocked. That's spectroscopy. The camera takes a picture of the spectrum of light. So each pixel in the image records how many of the arriving photons have a wavelength within a particular range. Sorting the photons by wavelength is a very powerful technique for understanding the nature of a light source. For example, we can check if the light has a Planck spectrum, and if it does, we can measure the temperature of the source. Modern spectrographs differ in detail from that simple prism and camera design. Instead of a prism, they're more likely to use a diffraction grating. That's a series of regularly spaced grooves in an otherwise flat surface, and the grooves have a different reflectivity from the surrounding material, so that when a light beam bounces off, the reflections from the stripes interfere with each other in such a way that the direction of the reflected beam depends on wavelength. Here is a spectrum of the sun, recorded by a spectrograph with a diffraction grating. You can see the full rainbow of colors, but if you look closely, you'll see that it's punctuated with thin, dark lines. We can get an even better look at those lines with an Echelle spectrograph, which has even higher resolution. It uses 2 diffraction gratings to spread out the spectrum in 2 dimensions so that you can read it like a book. Photon energy increases as we go across from the left to the right, and then when we reach the end of a line, we go down to the next line. Apparently, there are certain colors missing from sunlight, certain wavelengths at which the sun looks darker than usual. We'll see later that these spectral absorption lines teach us about the composition of the sun and the conditions in its outer atmosphere. Now, on to the fourth reason we love telescopes: to improve our temporal resolution, our ability to measure the time of arrival of a burst of photons, or any more gradual variations in their rate of arrival. As I mentioned before, our eyes have a sort of built-in exposure time of about 1/10 of a second. That's why movies work. We can watch a series of still images that's changing every 20 milliseconds, and be fooled into believing that we're watching continuous motion. For astronomy, a fixed exposure time would be a severe limitation. Cameras allow us to choose whichever exposure time is most appropriate for the purpose. With short exposures, we can watch events that happen quickly, like slow-mo movies. Today we have cameras capable of capturing scenes on the scale of milliseconds or even microseconds. This has led to the discovery of all sorts of fascinating, rapidly varying sources. For an example, let's look at the Crab Nebula. This splotch of color marks the site of a core collapse supernova, the explosion of a massive star. The light from the explosion first reached Earth in the year 1054 and was bright enough to see in the daytime, as attested by ancient Chinese records. What the Chinese could not know, though, is that at the center of this nebula is a star that blinks periodically, and the time interval between blinks is only 33 milliseconds. I'll have more to say about this extraordinary object, a neutron star, later in the course. Cameras also allow us to accumulate light for much longer than our eyes to build up a high signal-to-noise ratio. One of the best examples of the power of such long exposures is the Hubble Extreme Deep Field. For this project, which was one of a series of deep fields, astronomers pointed the Hubble Space Telescope in a more or less random direction in the sky, away from any bright stars or other known light sources, and gathered photons for a total of 50 days. The reason was to try and detect the most distant possible galaxies in the universe, which are sending just a trickle of photons to the Earth. The resulting image is studded with thousands of galaxies of all different shapes and colors, each of them with trillions of stars, all located billions of light years from the Earth. It's like staring into infinity. And remember, this was a random direction. These galaxies are everywhere in all directions. So, to sum up, the best way to think of a research telescope is a machine for measuring the properties of photons from celestial bodies. And what are those properties? The direction it came from, its energy or wavelength, and the time of its arrival. For completeness, I should add one more thing. Its polarization, one of a photon's wave-like properties. The polarization is the direction in which the electric field of the wave is oscillating. We won't have much occasion in this course to discuss polarization, but I wanted you to know about it. Another thing I think you should know is the traditional system of units that optical astronomers use to measure the flux of a source, the power per unit area arriving at the Earth in the form of light. It would be logical to express flux in some kind of standard metric units, watts per square meter. But we hardly ever do that. By hallowed tradition, we use a different scheme called a magnitude scale. The apparent magnitude, little m, of a source is defined as minus 2.5 times the log base 10 of the flux relative to a reference flux, F0. By this point in the course, you can appreciate why it's a logarithmic scale. It's to keep the numbers manageable, even though we deal with fluxes that range by many orders of magnitude, from nearby stars and planets to the most distant galaxies. It's the same reason we use the Richter scale for earthquakes and the decibel scale for sound waves. Those are both logarithmic scales too. But why the minus sign and the 2.5? And what's the reference flux? Let's start with the easiest one, the reference flux. The choice was made to set F0 equal to the flux of Vega, a bright star in the northern sky. That way you don't have to worry about calibrating your camera to measure starlight in watts per square meter. you can just compare the flux of your star to the flux of Vega. And then if you ever want to convert to standard units, just look up the flux of Vega in watts per square meter, which somebody somewhere has already measured. What about that minus sign? Because of that, brighter objects have lower magnitudes. It makes the magnitude scale like a ranking system for flux. A first magnitude star is brighter than a second magnitude star, which is brighter than a third, and so on. The 2.5 is a little harder to explain. When we invert the magnitude equation, we find F equals F naught times 10 to the minus 0.4 times m. So a star with 0 magnitude has F equals F naught. That is, the star has the same flux as Vega. And a star with magnitude 1 is fainter by a factor of 10 to the minus 0.4, or about 40%. If we go down to a 5th magnitude star, F equals F naught times 10 to the power minus 0.4 times 5. That's 10 to the minus 2, 100th. The lesson is that by increasing the magnitude 5 units, that corresponds to lowering the flux by a factor of 100. That convention can be traced back to the ancient astronomer Hipparchus of Nicaea from the 2nd century BCE. He created a star catalog and ranked the stars from 1 to 6 based on eyeball estimates of brightness. His catalog was influential and widely used by astronomers for centuries. Nearly 2,000 years later, we know the human eye has a logarithmic response, so Hipparchus's magnitude scale was a logarithmic flux scale. And as it turned out, the stars he ranked 6th magnitude are about 100 times fainter than 1st magnitude stars. The subsequent mathematical definition of apparent magnitude reflected a desire to match the ancient star catalog of Hipparchus. Yes, it's unnecessarily complicated and highly idiosyncratic, sometimes drives me crazy, but I also think it's kind of neat that the magnitude scale has this connection to ancient history. We can also use magnitudes to represent color in addition to flux. One way to quantify the color of a light source is to measure its flux through a colored filter, say blue, that only admits short wavelength photons. Then measure its flux through a red filter and take the ratio, FB over FR. Objects that are intrinsically blue will have a higher ratio than red objects. The color index is defined as the difference between the two corresponding apparent magnitudes. When we write that difference in terms of fluxes, using the definition of apparent magnitudes, and then use some standard log properties to rearrange things, we see that the color index is a logarithmic scale for that flux ratio, FB over FR. For this pair of filters, a high color index means a high blue magnitude relative to red, and because high magnitude means faint, a source with a high B minus R color index is relatively red. One more thing about magnitudes. We can use them to represent luminosity in addition to flux. Remember, luminosity refers to the intrinsic power of a source, independently of its distance from the Earth. For a source at distance d that emits in all directions, the relation between luminosity and flux is F equals L over 4 pi d squared. Well, instead of expressing the luminosity of a source in watts or as a multiple of the sun's luminosity, sometimes we express it as an absolute magnitude. That's defined as the apparent magnitude the source would have if we could magically reposition it to be 10 parsecs away. 10 parsecs is an arbitrary choice. The point is that if we put everything at a common distance, then the differences in apparent magnitude signify differences in luminosity. Usually we use little m for apparent magnitude and capital M for absolute magnitude. To find the relationship between them, first we need to compute the flux the source would deliver to the Earth if it were parked 10 parsecs away. Let's call that F10. Since flux is proportional to 1 over distance squared, F10 is equal to the actual flux, F, times d over 10 parsecs squared. Then we form an apparent magnitude based on F10. We divide by the reference flux, take the log, and multiply by minus 2.5. That's the absolute magnitude, which we now see from the right side of the equation is equal to the apparent magnitude minus 5 times the log of d over 10 parsecs. That's all I want to say about magnitudes. But that's not all I want to say about telescopes. In this lecture, we mainly discussed observations at visible wavelengths. But one of the best things about telescopes is their ability to detect invisible photons. Our eyes, it turns out, give us a very blinkered view of the cosmos. In the next lecture, we'll discuss how radio and X-ray telescopes broaden our perspective.